Hello! Today we start talking about the last unit in the course, and it's Unit A, and A is for applications. So the first application that we're going to look at is called optimization, and this is where you have a situation and you're trying to figure out everything so that you can spend the least money, or figure everything out so that the area is as big as it can be, or figure everything out so you come up with a pop can that holds the most pop, or something like that. So we're using calculus to try to find ways to optimize certain situations. Okay, so let's look at a situation, and then we will look at sort of the math behind it and how we can use the idea of the derivative to help us solve the problem. Okay, so the first problem is this one. So the problem is that we want to build a fence, and one side of the pen is a building, and so we need to use some kind of fencing material that goes from the building out to here, down to here, over here, back to the building, and we want to come up with the dimensions of the fence that will give us the maximum enclosed area. Okay, so we want to maximize the area. The thing is that we only have 100 feet of fencing to work with. Okay, so we have a function that we want to optimize. We want the area enclosed by the fence to be as big as it possibly can, but we only have 100 feet of fencing to work with. So how can we do this? First, I'm going to bring in some variables. So if the width of the enclosed area is, say, x, and the other dimension, the one that runs parallel to the building, if we call that y, then the function that we want to maximize, so maximize, oh, that's right, max, okay, a for area is equal to x times y, okay? And then in terms of x and y, how do we write down that we only have 100 feet of fencing to work with? Well, if this is x, then this is x also, right? So this x and this y and this x can't be any more than 100, and I'm going to assume that I'm going to use all 100 feet up, okay? So I want to maximize this, and we know I'm going to write subject to a constraint. And the constraint is that we only have 100 feet of fencing, and so that's 2 x's and y. I'm assuming that if I use it all up, then that'll be the maximum area of the fence. Okay, so this is it. And this is the way this works. If I have a function and I'm able to graph it, and I want to find the place where the value of the function is the biggest, that's like up here, right? And we know that if the function is continuous and kind of a smooth curve, that should correspond to a place where the derivative is 0 because the tangent line is horizontal, right? So that's the idea here, is that we want to maximize or minimize whatever the function is by finding places on the graph of the function where the derivative is 0, because that means you're either at the top of some kind of hill or you're at the bottom of some kind of valley. Does that seem reasonable? Okay, so the thing is that the function that we have here now, it's got an x and a y in it, so I don't know how to deal with that, but this equation that we have here that relates x and y, we'll solve this equation for one or the other of the variables, and then use it to write this function all in terms of one or the other of the variables. Let me show you what I mean. We could write this relationship here as y is equal to 100 minus 2x, right? And if y has to be equal to 100 minus 2x, then I can take this and plug it in there, right? And then I can write a all with just x's in it. So after I do that, I get that a, and now it's a of x, right, is x times this x times this stuff, 100 minus 2x. So that's the function that gives me the area of the enclosed region here. And I want to find out when this is the biggest, so I'm going to take the derivative of it. Before I do that, I'm going to multiply this x through. Right, so there's a of x. And what do I want to do? I want to maximize the area, so I want to look for places on the graph of A where the tangent line is horizontal. That'll either be at the top of one of these, or the bottom. We already talked about this. Okay, do you understand what we're doing? Okay, so differentiating this. The derivative of 100 times x is just 100, and then if I pull this 2 down here, I get minus 4x, right? So there's the derivative, and I want to know when, where, if it's ever equal to 0. So I'm going to set it equal to 0. And solve the equation that I get. And here we just have that 4x is equal to 100. So x is equal to 100 divided by 4, which is 25. Now, how do I know that the number that I have found here, how do I know that that corresponds to the top of a curve and not the bottom of a curve, right? Because this would be a minimum and this would be a maximum. And there's several ways to answer the question. The easiest way in this particular case is to look at what A is. A is a parabola, right? And since the squared term is negative, I know it opens down. And so if I'm finding a place where the derivative is equal to 0, it must be this place, right? So that's one way. In this particular case, but the way to do it in any case is to use your calculator. So if you look at the graph of 100x minus 2x squared. In fact, let's take a look at it right now.
And so here we have the graph of 100x minus 2x squared. I've got the window set so that x goes from negative 10 to 60 and y goes from negative 10 to 1600. I played around with this to get a pretty good picture. So the graph looks like that. And if we want to see the place where x is equal to 25, if we just go to value, then we see that we really are at the maximum point.
So the max occurs when x is equal to 25. What is y when x is equal to 25? Well, go back here and find a relationship between them, or you could look at the picture. If this x is 25 and that x is 25, then we've used up 50 feet of the fencing, right? And so y would have to be equal to 50. So that's when the max occurs, and the maximum value or area is what you get when you multiply the two of these together, so 1,250 feet. So this is the kind of problem actually that we're going to be doing in the next lesson. But I just wanted to lay this out for you. It's a pretty simple problem, and so what we're going to do, particularly here, is just look at this part. Starting with this and doing what we did here, and we'll get back to the situations in the next lesson. But for now, we're just going to talk about how to do the math. Okay? Okay. So here we're just looking at a function and talking about how to find the maximum and the minimum points. And I know the calculator will do this, but we want to use calculus to do it. And the result that we get should line up with what our calculator is telling us. Okay? So find the maximum min of this thing. So we'll take the derivative, we'll set it equal to 0, and we'll look for the places that cause the derivative to be equal to 0. Those are going to correspond to the bottoms of the curves and the tops of the curves like this. So the derivative, so we take the derivative and we set it equal to 0, and in this case we get a quadratic. And I think this one is factorable, so if we divide everything through by 3, that stuff inside the parentheses factors. And it factors like this, right? Because negative 8 times positive 2 gives a negative 16, and then negative 8x here plus 2x gives a negative 6x. And so this thing is equal to 0 when x is equal to 8, or when x is equal to negative 2. Okay? So the question is then, which of these is a maximum and which is a min, or are they both maxes, or are they both mins, or what the heck? And we can tell by looking at the graph of the function and locating these points. So let's look at the graph right now.
Okay, so here we have the function, and if you're playing along at home and you want to know what my window looks like, I've got it set like this. And here we see the graph of the cubic. And then we came up with x values that made the derivative equal to 0 at negative 2 and at positive 8. So let's just check those out real quick. If I go to value and punch in negative 2, I can see that that corresponds to a maximum over here. And doing the same for x is 8. We see that when x is equal to 8, we're down at this lowest part of the curve right here. So calculus, once again, works.
So I just wanted to make a little point about the difference between a local max or a min and what they call a global max or a min. The max and the min that we found here, doesn't the graph look like this? Yeah, kind of. So this is where x is equal to negative 2, and this is where x is equal to 8. This is a maximum. And this is a minimum, but they're just, this point it has a larger value of the function than anything else in its area. But is it as big as the function ever gets? No, right? Because the function continues to get infinitely big as it goes out to the right. And likewise, this is a minimum in this area, but it's not the smallest that the function is ever going to get because it keeps going like this, okay? So in this kind of case, we call this a local min and a local max. So what does a global min or max look like? Well, a parabola that opens up, this is a global minimum, right? Because that's the smallest that the value of the function is ever going to get. And if a parabola opened like this, then it would have a global maximum. You could have some of each. So you could have a function that looked like this. Let me get more pronounced. There's a minimum here and a minimum here and a maximum here. This is a local max, right? Because the values of the function continue to get bigger. This point over here is a local min because it's not the smallest point anywhere on the graph. And then this point right here is a global min. Okay, generally students don't have a fantastically difficult time with talking about the difference between a local and a global max and a min. It's just, they're the words that we probably would have used anyway. So wanted to mention that. Let's look at another problem. Well, actually, before we look at another problem, let's think about this. So what have I written here? The maximum and minimum values of a function occur when the derivative is equal to 0, and that's what we've seen here, right? The top of the hill or the bottom of a valley, I guess you could say. But they could also occur at a place where the derivative doesn't exist, and not always, but you could have like a cuspy point thing, right? So there's a max here, and a min here, and a max here, right, corresponding to a cusp. So we just want to extend this a little bit just to say, oh yeah, well you could have a max or a min at a cuspy point too. So when we take these two things together, these are called critical points. So when you're looking for maximum points and minimum points, you're checking out the critical points. So we want to use calculus to locate the critical points and then classify each of them as a maximum or a minimum, or then it might be that you have a critical point that's neither a max or a min. How could that happen? If you have a curve that goes like this, you could have a tangent line there that's horizontal, but that's not a max or a min, right? So optimum points, max and min points, will definitely occur at a critical point, but just because you're at a critical point doesn't guarantee that you have a max or a min. Does that make sense? Okay. Okay, so back to this example, what do we have? F of t is equal to t times 1 minus t to the fourth. Find the critical points and classify each of them as a max or a min or neither, and then say whether the max and min points are global or local. So we need the derivative. And since f is a product, we need to use the product rule to find the derivative, right? Do you see the negative 1 on the end? That's coming from the chain rule, right? I bring the 4 down to the front here. 4 times 1 minus t to the third, but then I have to multiply that by the derivative of what I covered up, and the derivative, of 1 minus t is negative 1. Okay, So the derivative looks like this. Let's clean it up a little bit. So this will be minus 4t times 1 minus t cubed. And set that equal to 0. So I want to solve this equation, and when you're solving an equation and it's equal to 0, one of the easiest ways to do that is to write the other side as some things that are being multiplied. So I would guess that your tendency here is to want to multiply all of this out and gather up all of the terms and all of that, but that's going to take forever. Instead, I've got a big term here and a big term here. I can factor it. Factoring is the process of taking two things that are being added to, or three or more things that are being added up and writing them multiplicatively. And so if I look at this thing and this thing, do you see that each of them has a 1 minus t cubed in them? Do you see that? So we're going to pull it out. Okay? So 1 minus t cubed. And then what do I have left? Well, out of this piece right here, I took 3 of them, so I've got the other 1 minus t left. And then out of this thing, I took the 1 minus t cubed, right? I took all of that out, and so I've just got this left, minus 4t. And then if I combine what's in here, it's factored. Do you see where I got this 1 minus t, and then subtracting 4 more t's is subtracting a total of 5 t's. So it looks like this. So when is this thing equal to 0? Either when this part's equal to 0 or this part's equal to 0. So t is equal to 1 and t is equal to 1/5 are my two critical points, and so now I just want to determine which one corresponds to a maximum and which one corresponds to a minimum. We can look at the graph real quick, and that'll tell us.
So I've got the function loaded in here. And my first shot at graphing it, this is kind of hard to see what's going on. So I'm going to do a couple of things. I'm going to turn the axes off. So I'm going to get the axis out of the way. And that's in the Format menu. So I'll go down here and turn the axes off. So that'll help. And also, I want to adjust the window so that I'm zooming in more. So I want a tighter window for the Y part of the axis. So I'm going to change that, have it go from 1 to 1. Let's see if that helps any. Yeah, we could even go a little tighter to make the bottom and tops of these, to make it easier to see that this is a maximum here and that this is a minimum. So let's go from, let's do really like 1/4 to 1/4. Let's see what that does. Oh my gosh, look at that. That's beautiful. So that looks great. We got critical points at 1/5 and 1, right? So that corresponds to a maximum, and if we do it again and look for the critical point at 1, we see that that corresponds to the bottom of this piece of the curve here. So yeah, great.
So, so they're both local, right? Local min here and the local max. So part of the reason that we're doing this work is because we want to get all of our computational tools together so that we can do more problems like the fence problem. And when you're doing problems like the fence problem, you don't have to worry about every value of x in the world, right? Because you can't have, you know, negative 43 feet of fencing. So we'll be able to restrict the domains that we look at these things on. So let's practice doing that here. So let's do this problem again. But now let's restrict the domain to just the part of the t-axis that goes from 0 to 1. Okay? So if we do that, the little piece of the graph that we get, so this is the y-axis, here's 1/5. So now the picture just looks like this, and now on this interval we have a global max and a global min, right? So now if we just look here, this is the global max on this interval, and either of these zero is the global minimum, and it occurs either here or here. So if we restrict the domain, then we can talk about like what's the biggest that the function can be between here and here, the smallest that it can be between here and here, and we use the word global, kind of like we've shrunk the universe down, and so now we can talk about how big things are just on that interval. Okay, so on a closed interval, a continuous function will attain a max and a min. So a closed interval means a boundary here and a boundary here. Continuous means that to get from here to here, I'm not allowed to pick up my pen. Well, if I'm not allowed to pick up my pen, then to get from here to here, unless I draw a horizontal line, to get from here to here, I've got to get to the bottom, and then there's going to be some other point where I'm at the top, bigger than anything else, right? And where could those points occur? These optimal values, and so by optimal here I mean max or min, will occur either at a critical point, so the bottom of a valley or the top of a hill, or, oh, I erased it, a cuspy point, right? So if they'll either occur at one of those places, or it might be at the end point of the interval, which is what we had here, right? The lowest points were at the end point of the interval. So as long as you have continuity, you can always count on being able to find a max and a min on a closed interval, okay? So we want to find out the max and the min. G of x is x minus the log of x on the interval from 0.1 to 2. And we're going to use this theorem to do it. And so this is what it looks like. First, find the derivative and set it equal to 0 to get the critical points. The derivative of x is equal to 1. The derivative of log x is equal to 1 over x. I'm going to set this equal to 0. And this tells me that x has to be equal to 1. So x equals 1 is the only critical point. So there are 3 places that I need to look. I need to look at the value at the critical point. I need to look at the value of the function at the left endpoint of the interval and at the right endpoint of the interval. So let's do that. Since the log of 1 is equal to 0, the value of the function when x is equal to 1 is also 1. So which of these is the minimum and which of them is the maximum on this closed interval? Well, the smallest one is the minimum and the largest one is the maximum. So this is the min. And this is the max. And if we punch this up on the calculator real quick, we'll see that we are absolutely right.
So here is the function, x minus the log of x, and I've set the window so that we're just looking at the portion of the x-axis that corresponds to the interval given in the problem. And when we graph the thing, we see that the maximum is over here. It occurs when x is equal to the left end of the interval. I think that was 0.1, and the minimum occurs right here where x is equal to 1. So life imitates calculus, right? We are absolutely right.